Hello everyone, welcome to the lecture again. In this course so far, we have seen that if the external forces are given, then we can find out the reaction forces and of course, if it is a cable, then the tension along the cable. Today, we are going to learn that if the external forces in a member is given, then we can also calculate the internal forces by the analysis of equilibrium. Now, these forces are particularly the shear force and the bending moments. So, let us understand what is shear force and the bending moment. So, let us understand it by example. So, as I said, suppose the external forces are given. So, let us say I have a bar and let us say the bar is like this. And on this bar, let us say various external forces are acting. So, let us say this is F1, F2, F3, F4 and F5. So, these are the external forces and let us say we want to determine what are the forces that are acting on this at a particular area of this bar. So, let us say this is the cross section, let us say this cross section has an area of A, then to determine the internal forces or the internal force system which are acting on the cross section A. So, first what we should do is we should isolate this part. So, we must first isolate the portion of the bar on both side of section A. Okay. So, herein you can see that there are two parts. So, let us isolate them and let us look at the free body diagram of the top section first. Okay. So, let us look at the free body diagram of the top portion of section A. Okay. So, let me isolate it. So, we have the force, external force, which is F1, F2 and F3, and then because the whole body is in equilibrium, therefore, on this part there will be a resultant, let us say R, and then along a arbitrary line, let us say there is a couple CR. Okay. So, we have in this free body diagram, we have external forces plus the resultant force couple system of the internal force. Okay. So, note that this resultant R is acting at the centroid or at the center of this cross section, and this axis of for the couple that is also passing through the centroid. Now, it is convenient to write down this resultant R in terms of x, y and z coordinates. So, let us rewrite this. So, we have this cross section and then we have the centroid, and of course, we have force F1, F2 and F3. Now this resultant R I can write down in terms of the x, y and z coordinates. So, let us say this is the x axis, this one is the y axis and let us say this one is z axis. So, along the x axis let us say the component of R is P, along the y axis it is Vy and along the z axis the component of R is Vz. Okay. Now, we will also have the couple. So, along the x axis let us say the couple is T, along the y axis the couple is My and along the z axis the couple is Mz. Now, let us look at the physical interpretation of this P, T, Vy, My and Vz, Mz. So, let us first look at what is P. P is the component of the force that is perpendicular to the cross section. Now, this force is also called the normal force because it is perpendicular to the cross section. It has a tendency to elongate or shorten the bar. Now, let us look at what is Vy and Vz. So, this is the component of the forces that are lying in the plane of the cross section. Okay. And these forces are called the shear forces, and they has a tendency to shear the part of the bar. Okay. Now, we have couple T. This T is the component of the resultant couple that tend to twist the bar. Okay. So, therefore, this is also called the twisting moment or torque. Then we have My and Mz. These are the component of the resultant couple that tend to bend the bar, and they are known as the bending moment. So, we are interested in the shear force and the bending moment. Now, to calculate this, we also have to follow some sign convention. So, let us look at the sign convention. So, suppose I have a bar, and on this bar you want to calculate the bending moment and the shear force. So, what we do is we think of as if we cut this bar into two parts. So, let us say I cut this bar at this point. Now, on the left hand side of the bar, let us think that the shear force is acting downwards. So, this V is like this and the moment is in this direction. In this case it will be positive, and on the right hand side of the bar let us think that the bending force is V prime and it is upward, and let us say the moment is in this direction, then we can take this as positive sign. So, if the shear force or shear V and the bending moment M at a given point of a beam are as shown, then we take them positive. Now, let us understand these concepts by one example. So, let us say the question statement is following. So, suppose you have a simply supported beam AB and it has a length of L. So, of span L, which is subjected to a single concentrated load P, applied at its midpoint D, and we want to calculate what is the shear force and what is the bending moment on this. So, we want to compute the shear force and bending moment. So, first let us look at the free body diagram of the entire beam so that we can find out the reaction forces at A and B. So, let us look at the free body diagram of the entire beam. So, let me put all the forces that are acting. So, at point A we have a force in the y direction. So, let us call it R A. At B you have a force again in the y direction R B, and then at the midpoint which is D we have an external force of P. Now, from here you can clearly see that R A equal to R B equal to P by 2. Okay. So, now we got the reaction forces which are acting at A and B. Now, to find out the shear force and bending moment, let us assume that the beam is cut at a point C which is between A and D. Okay. So, let me cut the beam at this point. So, let us call this point C, and let us look at the free body diagram of both the part. Okay. So, on the left hand side we have point A, point C. At point A we have a reaction force of P by 2, and then at C we will have force V and the moment M. Note that I have taken the positive sign. So, therefore, V will be downwards and M will be upward, and if my answers are negative, in that case I will change the direction of V and M. Okay. Now on the right hand side, we have point B. Here the reaction force is P by 2 again, and at the midpoint, so this point is D, I have external loading of P, and over here I will have the vertical force V prime and the bending moment M prime. Now this free body diagram is for the region x equal to 0 to L by 2. Okay. So you can see from free body diagram of AC that V is nothing but plus P by 2, and you can take the moment about point C, and you can see that P by 2 into x. So let me take this length as x, this length as x. So P by 2 into x is equal to M. So therefore M is also plus Px by 2. So therefore both the shear and the bending moments are positive. Now let me plot this. So let me first plot the shear force. So this is x, and just now we have calculated that the value of the shear force is P by 2. So it is independent of x, and we have calculated this in the region between 0 and L by 2. So let me put here that this is my L by 2. So its value is constant. So we are plotting B, and the value was P by 2, and also let us look at the shear force. So the shear force was Px divided by 2. Now note that this is a function of x, and it will be a straight line, okay, which is passing through the origin. So let me say that this is my M, and this is L by 2. So it will just rise, and its maximum value will be at x equal to L by 2. So let me put x equal to L by 2 over here. So we get P L divided by 4. So that is the maximum value. This is P L divided by 4, and of course it will be like this. Now to calculate the bending moment and shear force in the region between L by 2 and L. So let us say x is between L by 2 and L. Let us take a point E over here, and let us assume that the beam is cut at this point. So now let us assume that the beam is cut at a point E, which lies between D and B. So now let us look at the free body diagram of the left hand side and right hand side. So we have point A, the forces that are acting at A is P by 2, and then at the midpoint, so this is L by 2, we have a point D, and at this point the external force P is acting. Now at this end, let us take the positive convention. So we have bending moment M and shear force V, and on the right hand side we have point B, external force is P by 2, and this point is of course E, this point is also E. We have V prime force and the bending moment M prime. So this distance is, let us say, L, x, this we also know that this is L by 2. So, therefore, this distance will be x minus L by 2. Okay. Now, consider the free body diagram of AE. So, you can clearly see that V should be minus P by 2, because we have force V here and then we have force P and this force is P by 2. So, therefore, V will be minus P by 2 from summation Fy equal to 0. Now, to find out M, let us take the moment about E. So, we have force P by 2 into x equal to force P into its perpendicular distance is x minus L by 2 plus M. So, we got P by 2 into x equal to Px minus PL by 2 plus M, and this gives you M equal to P by 2 into L minus x. So, let us look at the plot of these. So, you can clearly see here that V is minus P by 2 in the region L by 2 to L. So, therefore, we have this equal to minus P by 2. Now, let us plot the bending moment. So, this bending moment, because of minus sign, it will come down, and if you put the value of x equal to L, in that case M should go to 0. Okay. So, this is the plot for the shear force and bending moment. Now, let us look at one more example. Here the problem statement is following. Draw the shear and bending moment diagram for the beam and loading shown. Okay. So, as we did previously, first let us find out the reaction forces, and for that let us consider the free body diagram of the entire beam. So, free body diagram of the entire beam. So, we have this beam. At point A, you have a external loading of 20 kilonewton. At point B, we will have a vertical reaction, let us say it is By. At point C, you have a external loading of 40 kilonewton, and at D you have a roller support. So, let us say the reaction force is dy, and this is 2.5 meter, this is 3 meter, and this one is 2 meter. To find out what is By, let us take the moment about D. So, we have 40 into the perpendicular distance is 2 meter plus 20 into the perpendicular distance is 3 plus 2 plus 2.5. So, which is 7.5 meter equal to By into the perpendicular distance is 3 plus 2 equal to 5. So, we get 16 plus 30 equal to By. Therefore, By is 46 kilonewton and its direction is upward. Therefore, we can calculate from the force balance equation dy equal to 20 plus 40 minus 46 equal to 14 kilonewton, and this is also acting upward. To find out the shear forces and bending moment, let us first cut the beam between A and B. Okay. So, we are interested first in the region wherein x is between 0 and 2.5, and let us look at the free body diagram of the left hand side of this beam. So, we have point A here, and at A I have an external force of 20 kilonewton. Let us say this distance is A, and over here there will be a shear force V and the bending moment M. From this free body diagram you can see that V comes out to be minus 20 kilonewton. So, that means I have to change the direction, and also M is minus 20 into x. So, therefore, both V and M are negative. Okay. Now, let us cut the beam between B and C, and let us look at the free body diagram again of the left hand side. So, this time we have this beam, we have this point A, and at A there is 20 kilonewton of force. At B we have just now calculated that there will be a reaction force and its value is 46 kilonewton. Now, here again let us say V is acting like this and M is like that. So, you can clearly see from the force balance equation 20 plus V is equal to 46, therefore, V will be 26 kilonewton. Now, to find out the M, let us take the moment about this point. So, we have M plus 20 into x. So, again this is x equal to 46 plus x minus 2.5, because this length is 2.5, therefore, this will be x minus 2.5, and from here we get M plus 20x equal to 46x minus 115, or M equal to 26x minus 115. Okay. So, this is in the region wherein my x is between 2.5 and 5.5 meter. Okay. Now, to find out the shear force between C and D, let us cut the beam like this, and here my x is between 5.5 meter and 7.5 meter. So, what is the free body diagram of the left hand side? So, we have a 20 kilonewton force, and then at 2.5 meter I have 46 kilonewton of force, and then so this is point A, this is point B, and then at point C I have an external loading of 40 kilonewton, and then let us say the shear force is acting like this and the bending moment is like that. This length is 3 meter and this is, let us say, x. So, therefore, this length will be x minus 5.5. So, from here you can see from the force balance equation that V is minus 14 kilonewton, because we have 20 plus 40 plus V is equal to 46. So, therefore, V will be minus 14 kilonewton. Now, to find out the moment, let us take the moment about this point. So, we have m plus 40 kilonewton into x minus 5.5 plus 20 into x equal to 46 into x minus 2.5 meter. So, we got m equal to 46x minus 115 minus 40x plus 220 minus 20x. So, this gives you m equal to 105 minus 14x. So, now let me summarize these results. So, in the region between 0 to 2.5, we got V equal to minus 20 kilonewton and m equal to minus 20x. Then in the region between 2.5 to 5.5, we got V equal to 26 kilonewton and m was 26x minus 115, and then in the region between 5.5 and 7.5, we got V equal to minus 14 kilonewton and m equal to 105 minus 14x. Let us understand it by the plot. So, let us say this is x axis and we are plotting V. So, first we have V equal to minus 20 kilonewton, and then it is 26 kilonewton, and then its value is minus 14 kilonewton. Okay. So, this is minus 14 kilonewton, this one is minus 20 kilonewton and this is 26 kilonewton. This is the plot of the shear force. Now, let us look at the bending moment. So, this is the plot of the M. So, let us look here between 0 to 2.5, it is minus 20x. So, therefore, it will be like this. And what is the maximum value of this M? Well, its maximum value will be at x equal to 2.5 meter. So, let me put x equal to 2.5. So, if you put that, you get m equal to minus 50. So, therefore, this is minus 50, and then in this region its value is 26x minus 115. So, it will go like this, and then in this region between 5.5 meter and 7.5, its value is 105 minus 14x. So, it is going to decrease because of minus x factor. Okay. Let us see here at x equal to 7.5. So, let us say x is equal to 7.5, you can see that m comes out to be 0. So, therefore, it has to pass through this. Okay. And let us look at the value over here. So, here my x is 3 plus 2.5. So, x is basically 5.5. Let us put x equal to 5.5 either in this equation or in that equation. You can see that if you put x equal to 5.5, then you get m equal to 28 kilonewton meter. So, therefore, this value will be plus 28 kilonewton meter. So, with this let me stop here, see you in the next class. Thank you.